All right, here we are back at part two. A couple things real quick. One, causation versus correlation we talked about. Just to give an example of that, I forgot to give an example that I had for you. At one time, they found women that were taking hormone replacement therapy, basically when they had hysterectomy or anything like that, and they were giving them estrogen or tablets that would help them make more estrogen. And originally, it was reported that that would lower their chances of heart disease or coronary disease, heart attacks and coronary heart disease. And so for a long time, they started recommending that hormone replacement therapy would reduce your risk of heart attack. So it's just one more benefit that it offered to the women. However, when they went back and looked at it, even though there was a correlation, yes, people on hormone replacement therapy seem to have less heart disease overall, they started grouping people together by some of the subgroups there. And what they found is actually hormone replacement therapy, when they compared women on that compared to women who were not, actually had a higher risk of uh, heart attacks and coronary heart disease. What turned out, though, from the original study, what they looked at, even though there seemed to be a correlation at first, it actually improved. What they also found out, people who were on hormone replacement therapy were also more likely to be better off, have better insurance, better diets, and better exercise routines. And those things were probably what was actually causing reduced coronary disease. When people eating the same type of diet, same type of exercise levels, and so forth, were compared to each other, it was found that the women on hormone replacement therapy were more likely to have risk of heart disease. And so that's an example of how there can be a correlation, but maybe not for the reasons you think. Okay, they were being correlated as being hormone replacement therapy having less heart disease, but it was because those same people that could afford to have hormone replacement therapy were more likely to exercise more and have better diets and a lot of the things that go with that, better health care and so forth. So there can be a correlation, but it may not actually be what's causing the effect that you're noticing, in this case, lower heart disease. All right, so that's just a little bit about that. All right, we've been talking about scientific method. They need to be repeatable and they have to be testable. If it can't be testable, then there's no way to really know if it's true or not and to do the scientific method. We also said the scientific method, we have steps, but in real life they don't always go through all those steps, or they may have to go through many more. Medical studies, for example, have clinical trials, and they have to go through, can be years and years, 10 to 15 years of clinical trials before the medicine can be released, because it's going to be given to people and going to have big effects in their lives and so forth. So there's some pretty strict standards. But a lot of times people that are scientists that have made great breakthroughs have done it more just great insight. All of a sudden, these the great ideas that came to them, or they just noticed something by accident. For example, penicillin is one of the classic ones. Sir Fleming, Alexander Fleming, I believe, was growing bacteria in a lab, and some of his probably just got contaminated, has some fungi growing in it. Okay, he could have very well have just thrown those plates out and said, well, let's start over again. These are all messed up. But he let them grow, and he noticed that around the edges of the fungus, it was killing all the bacteria right around that edge. And so well, what's going on here? And so he investigated it, and it turned out that that fungus was producing penicillin. Penicillium is the fungus, and it was producing something called penicillin, and the penicillin was actually killing the bacteria, which makes sense because bacteria and fungus both eat dead stuff. And so if a fungus can kill bacteria, then that means more for it to eat. So that's a good thing. And eventually that's where the invention of penicillin or discovery of penicillin came from, and eventually became a great lifesaver, and that many people, particularly in wars and so forth, but more people died from infections a lot of times in wars than from the actual fighting. And so that greatly increased the survival of people with injuries, either in wars and hospitals and so forth, and basically was the birth of antibiotics as we know. Now, just for the record, Sir Alexander Fleming, even though he discovered it, eventually gave up. He could not figure out any way to produce it in a usable form, mass producing it. I believe actually gave away the rights to that, and someone else came along and eventually did make it in a form that could be easily reproduced and taken by people, and because of that we have all the antibiotics we have today. But once again, it was not that, oh, he set out to discover antibiotics, but it was more just one of those things that he just happened to have a contaminated petri dish. But because he noticed that, and rather than just throwing it in the trash, he had that scientific frame of mind. Why is it doing that? And once again, he was curious, and so he did more experiments. And so in a sense, he did end up using the scientific method to do that also. All right. All right. Now, Albert Einstein had a famous statement he made, or a famous statement that he had made. He probably made many, but it says, "No number of experiments can prove me right. A single experiment can prove me wrong." All right. And his point is this, that he can do a lot of experiments, they all seem to support his experiment, but if someone else does an experiment that gets different results than his, or the opposite results, then something must be wrong with his experiment, okay? Or one of the experiments must have something wrong with them, or there's more to it than what they knew already. And so usually scientists do not say, here's what I think will happen. For example, let's go back to the tomato plants with fertilizer and tomato plants without. They don't say, oh, my hypothesis is that if I use the fertilizer, it will make a bigger difference, or it will make them grow more, okay? Instead, we do what's called a null hypothesis, okay? A null hypothesis, okay, is basically saying my hypothesis is that there is no difference between the plants with fertilizer and the tomato plants without. They will produce exactly the same, okay? And I can disprove that using statistics and using my results. If I can disprove that and say, nope, there's definitely a difference, then I can prove that, in fact, the fertilizer did help. But if my hypothesis is that, oh, it helps, it's hard to use statistics to prove that. So most scientists use what we call a null hypothesis. Null hypothesis just means that they say there is no difference between them. They're going to be the same. And then really what they want to do, if they're right, is they want to disprove that and show that, oh, there is a difference. And that, yes, the say, tomato plant with fertilizer did. Or, for example, if you had two cancer treatments, you would say, well, these two cancer treatments, the null hypothesis would be there will be no difference between these two cancer treatments. Okay? And then you would do the two treatments, you would analyze the numbers, and show, are they the same? Are they different? And if they're different, which one worked better? Okay? And so most scientists work from a point of, it's easier to disprove something. You can't really ever prove something. So it's easier to disprove something. So if we say they're the same, and then we disprove that, then we prove that, yes, there is a difference between them. It seems a little complicated and like an extra step, but it is an important part of science and an outlook of science. All right, real quickly, science and technology. Science, of course, is just the knowledge that we learn as we do these things. Technology is kind of entwined with that. Technology is basically the tools, the machines, the instruments, electronics, and so forth that come as a result of our science. And so it's fair to say that technology is an outgrowth of science. However, as we get better tools and machines and instruments, we can also do better science. So really they're hand in glove. For example, for many years, the study of disease was hampered by the fact that nobody knew there were such things as bacteria. And they didn't know there were such things as bacteria because they could not see bacteria. Once we had microscopes that allowed us to see bacteria, now we realize, oh, these could be causing problems, stuff. And we could do that. But without the microscope, we couldn't do that. But also, as we get better tools, those better tools help us to do better science. But also, microscopes were a function of people studying light and lenses and making better lenses. So science makes better technology, and better technology allows us to do better science. And so they kind of feed on each other. And one, science helps make better technology helps make better science, okay? And so they're very closely interrelated. All right. Now, the use of the technology and the use of the science is value neutral, I guess. Okay, it can be used for good things or bad things, and so that just depends on the people using it. Of course, that's also true of religion and a lot of other things. in life. It all depends on how people use them. All right. A lot of times scientists like to say, well, science has no good or bad, but sometimes that's kind of a sidestepping issues because when you make something of science, you have to bear a certain responsibility for how that's used. And so, and a lot of times they say, well, like religion causes wars and all this other stuff. And yes, it can and has. But so can a lot of other things. And they're not just good or bad. But science also is like that. Is a atomic bomb good? Well, I would argue no, but yes, it did end the war sooner. It saved lives, and if we hadn't developed it, very likely that Nazi Germany had developed it. Well, that would not be. I don't think anyone really thinks that would have had a good outcome either. So, science and technology are not good or bad. They're really just more of an outgrowth of how they're used. All right, last thing I'd like to talk about, and this is really the last thing, although I tend to say that a lot. Physical science. What do we mean by the physical science? Since this is physical science, what are we going to be studying? Well, the quickest answer to that is everything but life science. All right, biology and living things, all the related things like that will not be covered. But really, all the other sciences are called the physical sciences. Starting with physics. Physics usually has to do with forces, motion, light, magnetism, electricity, some of these things. It's considered in some ways a more basic science because all those things are involved in the other sciences. Physicists are people who discovered a lot about how the atom works, which of course affects chemistry. And then of course we're made out of atoms, so it affects biology and how living things work. Our eyes use the laws of lenses and light and how it's reflected and refracted into our eyes. So physics is kind of the basic of how does the world function and what are the rules and the basic rules that control the forces and of matter and stuff and how it all works. Chemistry is more how does that matter combine with other things and how does it interact with each other. Energy and matter, we usually say. Geology is more the earth, earth layers, earth materials, things that are in the earth. Meteorology is more weather, the atmosphere around the earth, and then astronomy would be anything outside the atmosphere of the earth. And so basically everything in the world and the universe is affected and covered in some sort of area of physical science. All right, this first semester will be almost totally in physics, and then next semester we'll get into chemistry, geology, meteorology, and hopefully also to astronomy at the end. So that's just kind of an introduction, getting going here, and we'll see you on Thursday.